Right. All right. Yeah. So today it's our great honor to have Kyle Jemison from Princeton to give us a talk at our OSU IoT seminar series. And the title of the talk today is Smart Surfaces for Next-Gen and Satellite Millimeter Wave and Ku-band Wireless Networks. So, Kyle is a well-known researcher and a full professor of computer science at Princeton University, and also has many of the achievements in the area of wireless networking and communication. His primary research focuses on mobile wireless systems, not only for sensing, localization, but also for communication, and especially on those massively parallel classical and recently the quantum and the quantum inspired structures for next generation wireless communication systems. So Kyle has many awards. He is, he has received this Google Faculty Research Award and this prestigious ACM SIG Mobile Early Career Award in the SIG Mobile community. And he is also a senior member of ACM IEEE. So without further ado, let's give the floor to Kyle.
Okay, thank you, Mi. Thank you for the kind introduction. And I'll just add that my lab at Princeton that I run is PAWS, the Princeton Advanced Wireless Systems Lab. And so you can go to paws.princeton.edu and see more about our research. But today I'll as Mi mentioned, I'll talk about the smart surfaces for next generation and satellite networks. So first I'll start off with an introduction to smart surfaces and kind of our vision of how smart surfaces will behave. Then I'll kind of segue into the millimeter wave domain. So this is a smart surface that is targeted at 5G millimeter wave frequencies up around 27 gigahertz. That's millimeter wall. That's our project. And then finally, I'll wrap up the talk with a project that we're doing on low Earth orbit satellite communications. And there are a number of such networks that are being proposed. And we have a planned kind of smart surface that is work in progress. So kicking it off with introduction. So this is a typical kind of 5G, 6G network evolution scenario slide. And we see that demand for the 5G, 6G network continues to surge. And all that demand results in more and more bandwidth requirements from all these interesting new applications. So for some time now, we've been talking about virtual reality and augmented reality. And that's one application that is highly kind of capacity demanding. The smart home introduces lots of Internet of Things devices. And in those Internet of Things devices, this could be in the home or even in a smart city as well. And connectivity, what we term connectivity, is a key consideration there. So connecting to the network thousands and tens of thousands of devices in a certain geographical area places a different kind of demand on a bandwidth requirements of wireless networks. And then finally, we have all these machine-to-machine applications, robotic automation, smart grocery stores, automated shopping stores, robots in the warehouse, all kinds of really interesting applications. So all those demands are placing demands on the spectrum that is below 6 gigahertz. And so the 4G and 5G spectrum that was used previously and has been used and is currently being used lies below 6 gigahertz, but this is extremely limited and crowded spectrum for a variety of reasons. Other users are in this spectrum, and that constrains what can be done with data networks sub 6 gigahertz. And so there's a huge opportunity in the millimeter wave frequencies to break out of this crowded area, and starting at 25, 27 gigahertz and going all the way up to 60 gigahertz and beyond, is where the millimeter wave and eventually the terahertz frequencies for 5G are going to be located, or are being located as we speak. And they have this advantage that because of the higher frequencies and the less constrained spectrum allocation at these high frequencies, they have the advantage of enabling data rates that can scale far beyond the sub-6 gigahertz frequency bands. The challenge with these millimeter wave networks is that they are extremely vulnerable to blockage and obstacles. So here we're looking at the wall penetration of a 24 gigahertz signal, and we see that the wall penetration, depending on the composition of the wall, some of the walls will allow more signal to penetrate, some will allow less signal to penetrate, but there's a significant amount of wall blockage when you go to a non-line of sight scenario. And in addition, clutter indoors, such as filing cabinets, whiteboards, people walking around indoors, means that the ability of these signals to be blocked by, for example, human bodies is significant. So this is data from IEEE Comms Magazine article, and we see that a person walks in front of a 60 gigahertz transmission, and the blockage is at least 20 decibels. We see similar results at 25 gigahertz. So high losses and communication glitches is the result. And so the first smart surface I'll tell you about today is a surface we call MM-Wall. And MM-Wall is designed to overcome these types of challenging scenarios for millimeter wave networks. So the first kind of challenging scenario we have in mind is this outdoor to indoor scenario. So this is of interest to a lot of mobile operators. You have a base station outside a building, and you have a window, and the signal is going to go through the window and reach a user. Trouble is that exterior walls are extremely prone to block millimeter wave signals. And so it's a real challenge to bring outdoor service indoors. And so MM-Wall is a steerable surface that's electronically reconfigurable and electronically steerable. And this is kind of one of the key differentiators of MM-Wall compared to much other work, is that it's electronically steerable. And so when the user is not kind of within the straight line of sight to the base station outdoors, MM-Wall can steer that signal and provide or enhance out to indoor service. Indoors, we are thinking of a scenario that I mentioned before, virtual or augmented reality. So you have a user here who's wearing a virtual reality headset, and you have an access point indoors that's maybe operating at millimeter wave to provide a very fast stream of video to that AR/VR headset. But as the user moves around, obstacles and clutter are going to block that direct transmission, and other people as well. And so MM-Wall is going to be again, electronically reconfigurable surface that can relay and also reflect the signal at an angle that is not what we call a Snellian reflection. So Snell's law tells us the angle of incidence equals the angle of reflection for a normal material, but MM-Wall is an engineered metamaterial. And so what that means is MM-Wall can reflect at a different reflected angle than the instant angle. And what that means is that since MM-Wall is fixed on the wall, it can be useful to more users at more different locations. And also notice that this electronic reconfigurability is allowing us MM-Wall to kind of alternate between a transmissive or a refractive mode of operation, where we're bringing outdoor to indoor service, and that reflective mode of operation, where we're doing an indoor only service. And again, that's another kind of key distinguishing factor for our work. Outdoors, by virtue of kind of being mounted on a window, we envisioned that the same kind of reflective scenario can happen outdoors to connect different base stations, perhaps when outdoor clutter comes in between. And then finally, we have some considerations of using MMWall in the link establishment part of millimeter wave. So for millimeter wave transmissions, the kind of the top level information that you need to know about them is that they are kind of pencil thin beams if you have good enough antennas or beamforming. And so those pencil thin beams need to be established in the right direction from base station to user and vice versa. And so there has to be a kind of a search or a link establishment process in order to make that happen. And so MMWall can kind of aid in that search by taking the incident transmission and splitting it into multiple beams. Again, all electronically reconfigurable. And so summarizing that, all these properties that I've talked about are accessible kind of within milliseconds of response time because everything is done electronically. Okay, so the high-level picture of how MMWall works is that it is made up of these ribs here that you see that are controlled by a control unit that is connected by low voltage wires that is placed nearby. And then we have an incident wave that's coming into MMWall. And that incident wave gets modified by the ribs of that comprise the MMWall. So now I'm going to zoom into the ribs of MMWall here and give you a better idea of how those work. So I call them ribs because these are, as you see here, they're a Rogers board. Rogers board etched with metal on each side of the Rogers, and they're stacked up so that they are in line with the incident wave here as it goes into MMWall. And then I'm going to show you detail about each of the ribs in the rest of this slide. So looking now at one of the ribs in more detail. So it has a Rogers board, which is here in green, and on each side of the Rogers board, it has metal. And what's going on there is the metal is changing both the electronic field of the incident electromagnetic wave and the magnetic portion of that field. And so the two sides correspond to the two portions. And so what happens is that when the incoming incident wave strikes one of these ribs, we get to bias the resonator rings on each of the sides of one of these ribs using this varactor you see here. And we have a varactor on the electric side, which you see over here. And then on the back, which you see kind of faded out on the same board, that's the magnetic side. And we have another varactor here controlling the capacitance of that resonator ring. And so we apply different voltages on the varactors that you see here on the axes of this picture here that's telling us what the ring is doing to the incident wave. So the electric voltage applied is on this axis, and the magnetic voltage applied is here on the y-axis. So when we apply a different electric and different magnetic voltage, what comes out of the other side of MMWall is a refracted or a reflected wave that is modified both in amplitude or magnitude and in phase. So we're shifting the phase by one of these ribs, or we're calling them meta-atom groups here. So looking now, you can see that we have a wide range of phase shifts possible, and I'll have more to say about that in a second. And also we're seeing a wide range of magnitude. Here on the heat map, the yellow magnitude is a higher magnitude, it's close to 1. So you can see that in many places we're getting quite an efficient reflected or refracted transmitted wave out from MMWall. Okay, so that picture, that was one of the ribs or meta-atom groups. And then that picture gets repeated as we go to different ribs of MM-Wall. And we have the same thing happen from the incident wave to each of these ribs. So we have a number of ribs. These ribs are spaced at a fraction of the wavelength. And so even if you have a kind of a what we call a pencil thin millimeter wave beam striking MM-Wall, that beam will strike tens of ribs, and the result will be a superposition of the effect of each of the ribs on the transmitted signal. Now notice that the ribs are all the same. They have the same control voltage up and down the rib. And so what this means is that we get to apply a different voltage on each and every rib here of MM-Wall. And so we can apply different voltages, which result in different phase shifts to the outgoing signal of MM-Wall from each of the ribs. So what that means is we can use those phase shifts to do all of the beam steering that we know how to do from conventional MIMO antenna arrays. So when we shift the phase, in a second, I'll show you how we steer beams. The result is that transmitted wave can be electronically steered by biasing the different ribs, and it will go off in a different direction. And this can happen at very, very fine timescales because the control can happen at millisecond or lower timescales. Okay, so now diving into more detail, how does this work? So let's look at the unit cell response of MM-Wall when an incoming signal strikes one of these unit cells. So the circuit board is omitted here. And so we're looking at the magnitude of the unit cell response and the phase of the unit cell response. Okay, so notice we have 2 degrees of freedom per cell. We have the magnetic and the electric side control voltages. And so when we apply a 0 control voltage to the magnetic side and a 0 control voltage to the electric side, what we get is we get a resonant frequency, which is here, which corresponds with a small dip in the magnitude. And then if we look at the phase response of the ring, at the resonant frequency, we have this phase shift. And so below the phase, resonant frequency, we're at a pi phase to the of the transmitted signal to the incident signal. And then above the resonant frequency, we're at a minus pi phase. And in this transition region, we have a smooth phase shift. So that's really important. Okay, so now let's see what happens if we take one of the sides, the electric side, and we start to increase the control voltage on the electric side. So in this case, we're at 4 volts control voltage. So then we see the magnetic side, that resonant frequency is unchanged, but the electric side, the resonant frequency shifted due to the shifted frequency of the control voltage. That corresponds to a phase shift at the same resonant frequency, but now you see that the 2 phase shifts are not lining up. And what that means is they're not lining up and reinforcing each other, so they don't kind of traverse the same phase region all the way from plus pi to minus pi that we saw before when the control voltage is matched. And if we increase the control voltage on the electric side, we see this phenomenon even more. Same thing happens if we kind of fill in our grid of control voltages here, and we increase the control voltage on the magnetic side as opposed to the electric side. Exactly the same thing you would expect. The magnetic side increases in resonant frequency, whereas the electric side does not. But if we sweep the control voltage on both sides to match, what that means is the electric side control voltage will match the control voltage on the magnetic side, and the resonant frequencies will increase with each other. What that means is that when we look at phase shifts, the phase shift of the resonant frequency, you see gradually increases. So if we have a transmission that is sitting here in the gray region that we want to control, what we can do is we can very carefully control the electric and magnetic side control voltages, and we will kind of sweep or adjust this transition phase band within the transmission bandwidth of interest, and we will get a phase response that we can control directly. So this is us actually doing this, and this is what we call the Huygens pattern. And just to give you some context on Huygens metasurfaces, so this Huygens metasurface was proposed a few years ago in the physics community, but this is kind of the first work that has made this type of electronically reconfigurable Huygens surface practical for use that is on a real kind of three-dimensional surface that can interact with real networks, like MM-Wall. So looking now at the Huygens patterns, let's focus here on the transmission pattern. So transmission means incoming signal and refraction out the other side of MM-Wall. And here I'm showing you both simulation results in the left-hand graphs, and actually like experimental measurement results on a vector network analyzer on the right-hand side. And you see there's a pretty close match between simulation and a real implementation, fabricated realization of this. So now, like focusing on what's going on in the Huygens pattern, we said that we would be using the control voltages that are the same. So that corresponds to a kind of a sweep diagonally across the Huygens pattern. And the thing to notice is that something that was hinted on the previous graphs is that the control voltages, when you keep them the same, you keep efficiency largely rather high. The efficiency is high. That's indicated by the bright colors on this heat map. And you see that we're sweeping phase across the full 360 degrees of phase. And a similar pattern is possible in reflection, this time using different control voltages, but we have the same kind of, we can pick out points in the Huygens pattern that have both a high transmission and different phase responses to give us the manipulation of phase that we need. Okay, so one of the major challenges in this work was scaling these Huygens designs to millimeter wave bands. And this was kind of really non-trivial because these resonators, they're called split ring resonators, and they have been used extensively before at lower frequencies, typically microwave frequencies. We're talking about 2 gigahertz to 5 gigahertz and up, but not very much in the millimeter wave regime. And the reason is that getting the resonator to resonate at the right millimeter wave frequency, as we've seen is completely required, is pretty hard. And here I'm showing you a sensitivity analysis on the resonant frequency to show you why that's the case. So we're looking at what is the resonant frequency that the ring resonates at, and what's the relationship of that to the various dimensions of the ring. So we're looking at the radius of the ring, the gap of the ring at the end of the ring, and then the width of the trace that comprises the ring. And you see here from the sensitivity analysis on the left-hand side graph, you can see that the resonant frequency is most sensitive to radius or the size of the ring, unsurprisingly. So if you're going to be at millimeter wave, you had better be at a radius that is quite a bit less than even 1 centimeter here. So a ring for microwave frequencies, which would be up at 4, 5, 6 centimeters, is, if you kind of mentally extrapolate this graph down, is going to be nowhere near the resonant frequency that we need, up around 25, 27 gigahertz for 5G milliwave networks. And so we need that high, that small radius ring, which is really challenging to actually fabricate on a circuit board. So we got up there, And we got up there to a radius that we need. But then we also have a sensitivity of the rest of the design to frequency. So we look at the gap, and you see there's less of a sensitivity of the frequency to gap itself, but we also kind of manipulated the gap as well to get to the right frequency. And same with the width of the resonating ring. Okay, so we actually fabricated this, and here's a video that's playing now. And on the left-hand side, we can see where the resonant frequency actually starts to impact. So you can see when the left-hand side, we see an overlap of the resonant frequency control voltages, and that's going to get kind of called out in this video that I'm playing here. And when you see there's an overlap, you can see there's a phase discontinuity. So here, down here on the purple phase plot, you should be seeing a kind of a regular sawtooth pattern. But as we sweep the frequency, that sawtooth pattern, here you see it again, the sawtooth breaks. And what that means is that there's a phase discontinuity. And as you see here, this is a 10 by 10 centimeter prototype. This is one of our kind of mid-stage prototypes of MM-Wall, and we are doing a near field test. So we have our spectrum analyzer, and we have a horn antenna on either side of MM-Wall in this near field test. And you're seeing that it's really working. So we're getting that phase discontinuity and phase shift that I mentioned previously. Okay, so that's control over RF, but we want to be able to control the rings. And that was another big challenge of making MM-Wall, was actually allowing a control line network to operate over the surface that didn't in fact interfere with the rings itself. So if you do nothing, if you just have control lines that are next to your split ring resonators, then the control lines themselves are going to, since they have capacitance and inductance themselves, they're going to kind of become part of the resonator itself and change the properties of the resonator. And actually, they will destroy the frequency of the resonation. They will lower the frequency of the resonation, and they'll make the whole thing useless. So there needs to be some kind of radio frequency choke to block the millimeter wave signals that are interacting with the split ring resonator over here from interaction with the control lines. So we looked at a number of different ways of doing this. So plain old copper lines, I said before, they're going to result in destroying the properties of the resonator. We can use inductors, coil inductors in particular, to choke off the interactions. The problem there is all these components, as you saw, there's many, many ribs. And so we're trying to minimize the use of too many components. And also, so if we put too many components onto our board, then we're going to be actually physically kind of blocking signal. We want the major kind of feature of the board to be just the ring itself, ideally. So we want to minimize all the other components on the board for that reason. And so coil inductors are that. And also we considered having radial stubs and using additional circuit boards. And same reason, it's going to block the signal. And although it's easy to fabricate, it's going to result in worse performance. So we settled on this kind of unique meander structure that I'm showing you here. And what this meander does is it puts on the control lines so I'm showing you two sides of the board here, electric side, magnetic side, and I'm showing you the meander structure that control lines are meandering like you see here, and we've placed them so that they don't kind of overlap with each other on opposing sides of the board. And so this means that they are not prone to resonate with each other. So they have all the kind of properties that we desire. So we're minimizing the use of extra components. We're avoiding a large amount of extra copper on the panel, and a meander is really easy to fabricate. So the whole thing is actually kind of really practical to fabricate and build, which we did. Okay, so just to give you an idea of how this all steers a real beam, for those of you who are not familiar or less familiar with the beam steering, what this does, so I mentioned this is giving us ability to control phase. So what this means is this is a kind of a schematic diagram where we have the incident wave coming in from the bottom here, and we have each of the ribs or meta atoms here with a control voltage that's different. And the instant wave is striking those ribs, and with a different control voltage that results in a different phase shift. And so if we organize these phase shifts, what we get is we can mathematically derive a relationship between the progressive phase shifts on each of the rib and the angle of departure of the steered beam. And that is kind of standard angle of arrival, angle of departure, MIMO beam processing. And that results in a steered beam that is some angle theta that is completely electronically configurable. And so we call this an array factor, and there's some kind of standard math that relates the phase shifts to the angle of departure theta. Phase shifts would be phi. In addition, we can, again, same standard math, we can use different phase shifts and produce if we, by the principle of superposition, we can split the beam into multiple angles of departure by inducing different phase shifts on the meta atoms. Okay, so now going up a layer to the link layer, and we want to talk about how the base station is going to establish a millimeter wave link with the user, and how MMWall can help that. So the link establishment part of the 5G, and this is similar to 802.11 wireless LAN link establishment. Link establishment begins with the base station or the access point sweeping the beam in all directions. UE at first is not going to be able to detect the base station, and so the UE is going to signal the MMWall to sweep itself via some out-of-band control signal. So we're imagining like sub-6 gigahertz control that is co-located with the electronic control of MMWall. So then we can, because MMWall is electronically controllable, as the base station is sweeping, MMWall can be sweeping in order to, direct the beam that's striking MMWall to the user. Then the user itself, as part of beam establishment, user is also sweeping and scanning. So we have now all three of the entities, the base station, MMWall, and the user, are sweeping and scanning. So we have a cubic algorithm that's going to be establishing a link from base station all the way to user. So we've established that downlink. So now we have an alignment between MMWall and the user. So the nice thing about this arrangement is we have radio channel reciprocity with MMWall and in general as a basic kind of fundamental property of the radio channel. And so once there's been established a downlink transmission from base station to user, the user can then send its transmit beam in the direction of the receive beam, and MMWall using the same settings as well, and the base station using the same settings as well, can switch to an uplink configuration, and reciprocity guarantees that we established an uplink beam. Now I want to kind of rewind to the refractive kind of downlink establishment, and I want to point out that this algorithm that I told you about that was cubic in complexity, that was a kind of a greenfield backwards compatible algorithm where the base station doesn't know necessarily that MMWall is in the picture. And so MMWall is kind of operating unknown to the base station user, and it's making refractive link establishment possible, whereas it's possible that the wall itself would have blocked that previously. If, on the other hand, mmwall does know about the base station and vice versa, you notice that the base station and mmwall, in the common case, they're going to be static. And so if they have some protocol to communicate with each other, they can establish a link with each other and use that link in order to establish the beam with the user in just a linear amount of steps. So mmwall would then sweep to the user because the base station would know exactly where mmwall was, and there would be no need for that additional base station sweeping. So that would be, actually, I misspoke. So a quadratic number of steps. So an n squared number of steps is mmwall would need to sweep and the user would need to sweep without the base station sweeping. In addition, I talked about beam splitting with mmwall. So we can also enhance the link establishment by taking a transmission and splitting it into different directions. And so there's been work on kind of multi-armed beam establishment, not involving smart surfaces, but observation here is that mmwall can also contribute to that kind of beam establishment as a smart surface. By splitting the beam and searching multiple directions simultaneously. So that's kind of decreasing the constants of that cubic beam search. Okay, so I've kind of hinted about the implementation, but I'll tell you more about the prototype of implementation where we're currently at with mmwall. It's a 20 centimeter by 10 centimeter prototype, but we note that it's quite scalable with the addition of more ribs. And we notice that each of these ribs is living inside and soldered to a control board on the upper and lower portions of mmwall. And that control board is taking control signals from a DAC, a digital analog converter, and applying those control voltages all the way down the rib, as you see here on the right-hand side. And those control lines are connected to each of the split ring resonators. So you see here that all of the split ring resonators kind of vertically share a common control. And what that means is we're steering in the azimuthal direction. So setting up the stage for our evaluation, I told you previously about the near field testing, but I'm about to tell you about the far field evaluation results. So in the far field, this is our lab here at Princeton, and fully realistic. So here we have an outdoor base station. It's a millimeter wave transmission. You can see it in the window here, sitting outside on the grass outside the building, and it's going to be transmitting into the windows and hitting mmwall in some instances when it's aimed. It's a horn antenna transmitter, horn antenna receiver. Here we have an indoor scenario. So we have now we brought the transmit antenna inside, and it's transmitting again, hitting mmwall to a receiver or directly to a receiver. So we have the outdoor to indoor scenario, and we have the indoor to indoor scenario that we're evaluating. Again, full realism, full office clutter indoors. Okay, so now let's look at the signal strength that we get both in the indoor to indoor and the outdoor to indoor scenarios. So here we have kind of a baseline. Here we're indoors to indoors, and we're looking at without mmwall, and we're looking at the signal strength of a bounce path. So we're saying here in these experiments, what if the direct path is blocked? What's the signal strength we're going to get from a bounce path? And you see for these graphs, you can see the transmit antenna location is the triangle here. So we have kind of two here transmit antenna locations. And then we're looking at receive antenna locations that are at various points indoors. And we see here that indoor to indoor, we have many places in our lab where we're getting really lower signal strength. So here on the left-hand corner, we're kind of blocked by a partition or clutter, and resulting in quite low signal strength, causing outages. Now looking over here at the outdoor to indoor scenario, here we have a scenario where we have the outdoors, we have the transmit antenna up here, and we have receive antenna positions that are measured down here. And you see that if we're not in line with a window of our lab, we're getting outages. We're getting very low signal strength. And then same thing with a different antenna, transmit antenna location here, we're getting outages again. I do see a hand. Let me take questions at the end of the talk, but thank you for the question. Okay, so now with MM-Wall, now we have MM-Wall and its steering transmissions, and you can see we have a marked improvement of the transmission reception signal strength. So we're changing outages to non-outages. And also notice that this is kind of working best when we're near MM-Wall, but it's also helping those regions that are not near MM-Wall. Same story, outdoors to indoors, you can see it even better here. So whereas before we were getting outages in these regions, here we're getting some signal. And the reason is that the signal's coming in, it's striking MM-Wall, and MM-Wall can turn the signal electronically and reach this non-Snellian kind of non-line of sight location indoors. And so we're improving coverage significantly. Indoor to indoor, now looking at kind of summary statistics. So we're looking at a CDF of the signal to noise ratio. So now we're kind of summarizing what kind of performance we get. And you see the environment only. If we don't have MM-Wall, we're looking at the environment. You see that many locations are in almost outage. So they're kind of falling below a 64 QAM data rate that an augmented reality setup would require. And so this isn't any good. And so with one MM-Wall, this is a paired CDF. So one of the CDF points actually corresponds at the same Y location to this scatter point of MM-Wall. And you can see that in many circumstances, MM-Wall is, or in most circumstances, MM-Wall, when the reflection path goes through MM-Wall, it's, improving signal strength by typically 10 decibels, as you can see here by the red points that are to the right of the environment CDF. You do also see here examples where the environment CDF is actually giving a better reflection path than MM-Wall. It doesn't happen too often, but it does happen when the angle is just right. And so this is, kind of full disclosure of the the instances, the experimental positions in space where MM-Wall, as you see here, the scatter point is to the left of the CDF, gives a worse performance. In that case, the beam search would fixate on the best signal to noise ratio. And so what the endpoints would do in these kind of less frequent cases is they would take the max SNR of MM-Wall or the environment. And so that's the plot we have here. And so this is very, this is what the beam establishment protocol of the endpoints does. And so the performance of MM-Wall with such a link establishment protocol would be what you see here in the max SNR. The max SNR is simply kind of discarding those data points that give worse performance, and by virtue of the link search. And this is just a kind of a digest of the signal to noise ratio gain that MM-Wall is providing. That is a digest of this data. And you can see it's ranging from 0 here. This is CDFs now we're looking at. 0 gain when the endpoints would choose the environmental path over MM-Wall, to up to almost 20 decibels of gain. So MM-Wall is pretty small. So it's 10 by 20 centimeters. So what we did was we did a kind of a trace-driven evaluation where we then took MM-Wall and we moved it to a different location of our lab. And then we said, okay, what would a beam search do if the beam search could go through either one of the walls? So this is the orange points I'm showing you now. So we have two walls, and you notice that hard to see on the scatter plots, but there are examples where the two walls, the ability to go through an wall at a different location is giving us a substantial signal to noise boost over wall in one location only, which is in turn giving us a substantial boost over what's possible in the environment. And so that is again summarized here in the SNR gain. And you can see here, adding another wall location is resulting in kind of synergistic gains, added gains over just one wall itself. And so that's pretty exciting to us because this is, 10 by 20 centimeter reflective surfaces. So we think it's pretty feasible to kind of stick these reflectors everywhere in a building, in a room, or many locations, and the additive nature of performance gives us kind of encourages us. One might ask, how would a simple metal reflector sheet do? So we took I think it was a kind of a 3 by 5 foot metal reflector sheet, and we ran the same experiment. So what's the SNR of between transmitter and receiver indoors if we try to bounce off that metal sheet? The metal sheet is subject to Snell's law, angle of incidence equals angle of reflection. And so what that means is most of the time, the metal sheet does not reach the receiver because the angle of incidence has to equal the angle of reflection to reach the receiver. And so you see that in the data, and you see that the metal sheet is not performing much better than the environment itself. And the environment itself is the walls primarily. And so just simply adding a metal reflector is not going to get you very much over just bouncing the signal off your walls, but the wall results are over and kind of beyond what you get by bouncing the signal off the walls. And that the reason that is the steerability. Okay, so I talked quite a bit about the indoor to indoor results, but just to summarize, the same kind of reasoning goes and holds in the outdoor to indoor. What's interesting there is you see that a lot of or a lot of positions indoors are in outage, -infinity signal to noise ratio, because they hit the exterior wall of the building, they can't propagate. But same story, wall is bringing those links that were in outage in an out to in scenario. wall is bringing those links into operation, and kind of same big potential gains. Okay, so I'll go kind of fast here, but we then looked at the possibility of blockage. And so we ran experiments where we blocked the wall path with some probability of beta. We also blocked the non-line of sight reflection paths with some probability beta. So as beta increases, that is, you can think of that as the probability of a person walking between the wall path or the room reflection path. So as beta increases, we have more and more outage, as evidenced by this -infinity SNR. And with 1 and 2 walls, same story. We increase signal to noise ratio, and we reduce the probability of outage. Outdoors to indoors, same situation. Even more marked kind of reductions of outage probability because we are able to steer the signal through a window to get to the user. All right, so I think I have about 5 minutes remaining, so I'm going to give you a quick breeze through low Earth orbit satellite networks and the use of smart surfaces. But I will note this is forthcoming at the ACM HotNets workshop So my student Casey Kunwoo Cho, she's the author behind, the primary author behind MMWall, and also this Wallio work that's coming out in HotNets. So there are many low Earth orbit satellite networks that are being rolled out. I'm sure you've heard of Starlink, OneWeb, and Telesat. There are others as well. Very exciting type of network that has potential to provide quite low latency connectivity to global locations. And so we are envisioning using these networks, and the companies are as well, in very challenging use cases. So transportation, you might have users on a bus or a train. And wouldn't it be nice to be able to steer signals from these satellites down to users and have them reach the users directly while they're moving at speed? What that means is that introduces challenges of getting the signal at the right angle and steering that signal and maintaining the signal strength to all those users. And that has to happen in a very responsive, electronically configurable way. In a city, we have an urban canyon scenario where we have satellites that are going to hit buildings, and it's going to be very challenging to receive signal when you're at a low floor of a building. In rural settings as well, we're going to bring that signal into the home for a user. We might not want to have a kind of an unsightly satellite dish outside the home. And so in each of these cases, we have these challenges that we think a smart surface can address. So in transportation, we talked about steering that signal to the users. In an urban canyon, same kind of concept as MMWall. If we have a surface on a building that can operate in that outdoor reflective mode and bring the signal down into the urban canyon to users in a city, and same thing of a surface that's on a skylight, perhaps of a house in a rural area. So we think there's real kind of potential for use cases of the smart surfaces indoors. And if we think also about the link establishment problems in these low Earth orbit satellite networks, these different satellites are handing over communication to a user from one satellite to another. And so there's potential to use the beam combining and beam splitting functionality to do the same thing. So these satellites are operating at the Ku band. So that's at between 10 and 14 gigahertz. And what they do is they use a frequency division duplex. So on the downlink, they're operating it in the lower Ku band. On the uplink, they're operating on those higher 14 gigahertz frequencies. And so what the surface is it's a surface that can operate at both those frequencies. And so these, what we have is we have resonator rings that can resonate at both frequencies. And this is really challenging because we have these different sized rings. So I mentioned before that the size of the ring is the kind of the primary determinant of the frequency. And so for low Earth orbit satellites, we have this downlink frequency that's way different than the uplink frequency. And so if we were to just kind of try this with varactors, then we get a situation where we have many varactors on a board, and we're kind of not being very efficient with varactors. And we also have interference between the resonation of the two different ring sizes. If we try and share the varactors in order to reduce the number of components, then we have a kind of an interaction between the shared varactors, and we don't resonate at both the downlink and the uplink frequencies. So we need some kind of choking off of the two resonant structures, which we can do with inductors. But again, we don't want to use too many components. And so what we do in the end is we use a combination strategy where on one side, the electric side, we use inductors to isolate the two resonant rings, and on the other side we use a meander structure to isolate the electric side resonation and between the two rings, and so we kind of get the best of both worlds in terms of resonating at both the downlink and the uplink frequencies. And here's kind of a cartoon that shows you the outside ring you can see here is resonating at that lower frequency at 10 gigahertz, whereas now I animate the inside ring at 15 gigahertz. The inside ring is resonating at 15 gigahertz. So we get to control both frequencies. All right, so I guess that brings me to the conclusion and the hour. So wrapping up, so I've told you about mmWall, and this was for NextG wireless networks, and this is bringing outdoor to indoor coverage and indoor only coverage, and the system is steering and beam splitting and frequency shifting almost 360 degrees, which is really a first for this type of surface at millimeter wave. And it's operating all electronically and in real time with a data network. And then I told you about the satellite data networks, and for more kind of information about that, Kun Wu, my student, will be talking at HotNets, so I encourage you to attend and hear her talk. And just to summarize, these are the first designs that we're aware of that realize the potential of Huygens surfaces at millimeter wave. And I hope I've convinced you that they're overcoming kind of fundamental challenges in RF design and control at millimeter wave. So with that, I'll wrap and take questions. And for more information, for all the papers describing mmWall and WALL-E, please go to our website, our group website, pause.princeton.edu. And with that, I'll say thank you to the organizers for having me at this exciting institute, AI Institute, and very happy to take questions.
All right, thanks so much, Kyle, for the fantastic talk. Any questions from the audience? I see Kaushik, please.
Okay, thanks, Kyle. Fascinating. So you are shaping the environment and you're shaping this for wireless signals. Now the question is, as you see the number of elements increasing, perhaps exponentially, do you see the role of perhaps machine learning or others to sort of dynamically reconfigure orientations despite, and you have to do this within the channel coherence time often. So any thoughts on that?
Yes, yeah, great question. So let me go back. I guess when you say elements, do you mean like elements of the surface, or do you mean base stations and mobiles?
No, elements of the surface.
Elements of the surface, yeah. So the answer is yes. So I guess your question was, could machine learning play a role in configuring the surface? And the answer is totally. And the reason is that it goes back to the Huygens pattern that I'm showing you here, right? So before I said that, you know, if we take refraction or transmission, this diagonal sweep results in a good amplitude, as you see here, because it's bright yellow, and it results in a phase shift that's a rainbow. That means it's a continuous variation of phase shift, so we can accomplish most of the phase shifts. But, you know, look, it's not perfect. So here in the middle, when we're getting to these green phases, maybe we do have less of an amplitude. So we're not getting as much signal if we really want to target those green phases. But you can see here that if we jump off the diagonal line, then we have areas of green phase, which is perhaps the desired phase, that might line up with these yellow regions here, or maybe, in this blue region here of phase, we want to use this blue region of this high transmission, high efficiency blue phase region, and use that to make a desired beam pattern. So what that means, coming back to your question, is we want to use any point. So we have a search problem. So because we have a search problem, hey, maybe machine learning, maybe we could learn so actually, like, not just machine learning, because in my, I know it's the AI Institute, so I know my response will disappoint slightly, but any search algorithm might provide added additional benefit. Yet I concede that machine learning search-based algorithm to learn that phase might be a very good candidate. So the answer to your question is yes, maybe machine learning can find these kind of off the beaten path points to use to construct a beam. And actually, let me be more bullish or optimistic about machine learning, because as we know from standard MIMO techniques, constructing a beam pattern that's kind of arbitrary is a search problem that machine learning is pretty good at. And so, like, adding the response of a smart surface to that search problem is actually, like, strongly reasons to be optimistic about using machine learning in conjunction with the smart surface to make that arbitrary beam pattern. So the answer is yes, and that's why. And we've looked at that. So Casey did run, my student Kunwu Casey did run a certain search algorithm. I don't think it was machine learning based, but that's definitely like our next steps. So great question.
Thank you. We do have another question from the chat box. Very interesting, exciting topics. So the question is, in the link establishment part, if the user is moving, does the MM-Wall need to reestablish the link? If so, how long will it take to reestablish the link? Thank you.
Sure, yeah, great question. So I'm trying to find my link establishment slide. Yes, okay, thank you. So yes, yeah, user is moving, and so these link establishment and link maintenance algorithms, they track the user as the user moves. So typically what you do is you'll do small continuous kind of perturbations of the beam to kind of search and maintain that high signal strength. Now, yeah, that's a beam maintenance, and then MM-Wall should be doing the same thing. So perturbing the beam as well to maintain the signal strength. So it's a great question. I didn't talk about that on this slide, but so one answer is that those small perturbations to maintain the signal strength, and that's what we call maintenance. And then if the user moves way too fast, or the user, like some person comes in between, right, that's going to completely cause an outage, and the user, and then we have several, so that what I'm saying is the link establishment may need to be re-triggered, or sometimes we form backup paths. So there might be a backup path that is either direct or through MM-Wall or through a bounce, and then we'll switch to that backup path. But I guess the key is that to answer the question, it's maintenance and then re-link establishment. But then the next step is, like, MM-Wall is giving you one more backup path, which is going to improve network reliability. That's a good question.
Thank you. Thank you, Kyle. So any other question from the audience? probably I'm going to ask the last question. I think. So, what is the range? Like, for example, indoor to indoor communication. How long the MMWall currently supporting?
Sure. So let me go to my slide. So let's see. So our transmitter here was 7 meters away. And here, I guess, well, the receiver was all over. So I would say, excuse me, I would say about 4 to 6 meters back. So in the performance results I showed you, that'll be about 13 meters of range. Yet, you know, we were getting signal to noise ratios that were pretty high. So I think we were pushing 30, 40 decibels of SNR. And so that means we have headroom to go back. And actually the only reason we didn't go back is because we're on the grass here, and then we have sidewalk, and then we have road. So that was honestly the only reason we didn't go back further, but I believe we could have gone back further. So our range is pretty good. Now, I guess full disclosure, so the antennas that we're using, these are pretty big horn antennas. And so again, we discounted our results so we actually discounted the results we were reporting here to reflect a lesser gain of something that's more realistic for a user device. But nonetheless, we have the headroom, and so we didn't feel very range limited. So, you know, these experiments, it's a great question. These experiments mostly test clutter and resistance, you know, routing around clutter. Probably we should test extended range scenarios as well. And I think that's an intention. Definitely with the low Earth orbit stuff, we'll be looking at a longer range, because it's important when you go to low Earth orbit networks to the range has to be, you know, tens to hundreds of miles. So that has to be a significant range, tens of miles. So yeah, we don't feel very range limited.
Thanks, Kyle. I think maybe there's going to be the really last question. So from the chat box. So I think this question is really about the extension from one to multiple MMWalls. So basically, the question is, if there are multiple smart surfaces in the room, will they create any interferences?
Yeah, it's a fair question. So so the great thing about millimeter wave is it's only kind of active. It's a passive surface, first of all. So there's no amplification, if you notice. And so that's actually a really cool thing about passive surfaces. There are other active millimeter wave designs. One is by Omidabari at Waterloo and UCLA, and Omid has an active reflector design where and there are other examples of that. So there's a potential there to add interference at millimeter wave. However, at millimeter wave, your beams are pencil thin. So even for the active designs of Abari, you're not going to really add interference, because you're only the surface is only reflecting or refracting when it's lit up by a transmission. And so there isn't, so this would be true at kind of microwave frequencies that are more omnidirectional. So 2.4 gigahertz, 5 gigahertz, sub 6 gigahertz, this would be true. But for millimeter wave, you have this, what we call spatial reuse. So, you know, it's only active when the pencil thin beam is pointing. So it's more like light, really. Or laser beams, you can think of in terms of how we think. So the potential for there's no kind of overall raising of the noise floor that we saw back in the work that's sub 6 and lower frequencies. So not too much of an issue.
All right, I think that would really be the last question. So thanks so much, Kyle, for the fantastic and very informative presentation. We really appreciate that. So this is probably going to conclude today's recording. I'm going to see you guys in the next seminar. Thanks so much, Kyle. Really appreciate that.
Thanks for
Bye.
having me. Bye-bye.
Bye.